In this video, we're going to learn a little bit about the Bohr model of the atom. So what I just did was I turned on a light and it's going into a box containing hydrogen. And this light contains photons of many different wavelengths. That's why it's called white light. And you can see we've got a green here, we've got a violet here, a red here, all going through. Um, and there's a big question mark here because we don't really know what is in the atom. That's the perspective that we're taking. Um, so what we do know is that as we observe the spectrophotometer, we're seeing little dots here. This just means that for every time a photon is released of whatever wavelength, a dot appears. So one just appeared here at around 490 maybe nanometers. These numbers are in nanometers. So yeah, we have one at around 490, another one at maybe 410. But notice more photons are being emitted that have a wavelength of around 90 to 100 nanometers. Um, and so long time ago in the mid 1800s, Johannes Balmer was experimenting with hydrogen. He was using a discharge tube, so it wasn't that he was shining light into the hydrogen. He was essentially putting electrical current through it. But what he found is that the photons emitted by hydrogen had very specific wavelengths, and that's what we're seeing here. Notice we're getting, I guess a few at around 490. A few at 410. One just popped up here at about 660. And more are popping up around the 100 nanometer wavelength. That being said, in the 1800s, these weren't really noticeable because they're in the ultraviolet range of the spectrum. Of course, the 400 to 700 or so, that was the range that was visible. And these are the ones that Balmer was looking at. If I were to leave this for a while, we would probably get four different wavelengths in the visible spectrum, around 660, around 490, 430, and 410. But it's really a probability game, and it's a weighting game. So we get those in the visible spectrum, and then we get a whole bunch of photons being emitted that are around 100. They look like they're kind of on top of each other, but they are very specific wavelengths. So what I'm going to do now is turn out the light, and I'm going to go to the different models that we had of the atom. So if we go back to, say, the classical solar system model, this is the model that was devised by Rutherford. And what we saw, I'll reset this one more time if I can, but what we saw is the electron is basically spinning. This is plum pudding, 1 second. Here we go. The electron is spinning around and around, and its radius gets smaller, and eventually it just crashes into the nucleus. And this makes a lot of sense because the electron is attracted to the nucleus, electron being negative, nucleus being positive. And this is a failing of Rutherford's model. J.J. Thomson, he created the plum pudding model when he discovered the electron. But in the case of the plum pudding model, the electron, negative, was in the middle of a sea of positive charge, that being the not nucleus. It's in the sea of positive charge. And so they weren't separate from each other. And that makes a lot of sense because opposites attract. The electrons and the positive charge should be close together. But when Rutherford was experimenting, he found that actually there's a nucleus in the center of the atom, and that's both where all the mass of the atom is and also where all the positive charge is located. So he proved this, but he couldn't explain why it is that if there is separation of the electrons being way outside from the nucleus in the middle, then why it is that the electrons don't just spiral into the nucleus. And this is where Bohr came in. So Bohr was experimenting with the same kind of stuff that Balmer had, but he ended up creating a model for the atom that makes sense. What we're looking at right now is an electron in the first shell. So Bohr came up with this idea of there being a first shell, a second shell, a third shell. And notice this isn't a path that just spirals into the nucleus. That electron is spinning around in a circle, very predictable, and it's not getting closer and closer and closer to the nucleus. Actually, I'm going to click this right here so that we can see the electron energy level. We can see that it's in the n=1 state. That means the first shell. And what we'll do is, if we were to shine light of all different wavelengths, we could, but we get a lot of different things happening. I'm going to put on monochromatic light, and I'm going to specifically tune it to 94 nanometers. And so now all the photons going through have a wavelength of 95 nanometers. And notice, I'm pausing it right now, notice that one of the photons was absorbed by the electron, and the photon has kinetic energy. It transfers that energy to the electron, and the electron goes from being in a low potential energy state to being in a high potential energy state. The absorbance, the energy absorbed to get from n=1 to n=6, that is the exact amount of energy as is contained in the photon that has 94 nanometers as its wavelength. So I'm playing the simulation again, and notice, now I paused it. So the electron dropped down from the sixth shell. Now it's in the third shell, and we can count 1, 2, 3. We can also see it right here. So it's in the n=3 shell, having dropped down to a lower potential energy state. But if it loses potential energy, it has to, for conservation of energy, it has to also emit some extra energy. So it's just like if I fall out a window, then I lose potential energy as I fall, but I gain kinetic energy in the form of my momentum as I'm speeding up as I get close to the ground. In this case, with electrons, the electron is similarly falling to a lower potential energy state, but instead of it gaining kinetic energy in the form of momentum, it releases kinetic energy in the form of a photon of light. And that's what we're seeing right here. This red, it looks red, it's actually infrared. And that's why you don't see it so much here, but that count should show up here somewhere. And notice it's going from the n=6 down to the n=3 shell. But it can still continue to drop further. It wants to eventually get down to the n=1 state. So let's play and see what happens. Oh, there it goes. And all right, it's tough to see, but it dropped from the n=3 down to the n=1 shell. And you can see actually right here, the wavelength that it released, it's just to the right of that 92 nanometer mark. We can see now it's here in the n=1 state. The photon that's emitted, you won't be able to see it distinctly here because, of course, all of the photons that are going through are in the ultraviolet range. I think it was this one that was emitted, but it's tough to tell. So anyway, I'm playing it again, and the electron just absorbed another photon because it was at the n=1 level, and now it goes up to the n=6. Notice the second time as we go down, oh, it also went down to the n=3 this time, and then down to the n=1. This pattern is not required. It can go down in many different patterns. It could go from 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. It could go from 6 to 3, 3 to 1. There are lots of different possibilities. What I'm going to do now is turn off the light and just allow the electron to drop down. Notice in this case, by the way, we went from 6 to 5 and then down. So there we go. Anyway, now the electron's in the ground state, the n=1. And we're going to change the wavelength. What we're going to do is we're going to make it 95 nanometers and see what happens. So the electron absorbs energy. 95 nanometers is going to be slightly less energy. And so, no surprise, the electron, instead of going to the sixth shell, it goes down to or goes up to the fifth shell, because it had less potential energy that it could gain from that photon. But similarly to before, the photon drops back down. It dropped down first to the fourth shell and now to the third shell. And each time it drops, it releases a photon with a very specific wavelength. So I'm going to turn off the light now. And I'm going to tune this to 97 nanometers once this decides to work. Come on, 97 nanometers. 90. No. Hold on. Sorry, computer is struggling with a. There we go. All right, so at 97 nanometers, this light is going to bump it up to the third shell. So we had 654. Sorry, it was at the fourth shell, and then it eventually dropped down to the third. So the photon, now it's in the second shell, and now it goes down to the first, and let's see it go up again. There we go. It's in the n equals 4 shell now. So it went up to the fourth shell. So just recapping, 94 nanometers of light had enough energy to bump the electron to the sixth shell. 95 bumped it up to the fifth shell. 97 nanometers brought it up to the fourth shell. Now you might be wondering about 96 nanometers. Well, I'm going to turn off the light, play the simulation again, and the electron will bump down eventually. And here we go. Now it's spinning around. So what I'm going to do is I'm going to bump it. I'm going to change the wavelength to 96 and turn on the light. And nothing happens. Nothing happens at all. And this is because if you consider the amount of energy in a photon at 96 nanometers, that energy is not exactly enough energy to bring the electron from the n equals 1 state up to the 2, the 3, the 4, the 5, or the 6th. It is in between the amount required to get the electron to the fourth level and to the fifth level. And because there is no n equals 4.5, for example, nothing happens. The light just passes through. And that's the case with most wavelengths. If we look at the spectrum right now, actually, there's a lot here. But these emissions that we're looking at, they represent photons with exactly the amount of energy that is equal to the energy difference between one energy level and another. So, for example, that one right there, that red at around 660, that is the exact difference in energy between the third level and the second level. And from the fourth down to the second, that would be the one that we previously saw at around 490. For the fifth down to the second, that's the 430. And so actually what I can do is I can tune this and I can say, all right, let's go with that 656. I believe it's 656.28, so it should round to 656 for the purposes of this experiment. So we're shining red light, and you can see the red photons are going in, and nothing is happening. Nothing is happening because the electron is in the first shell, and that's not enough. The light that's being shined is not enough to bring it from the first to the second level. But if we, for example, go with 121, and let's change this. That is exactly the energy required to bring the electron to the n equals 2 shell. Or, oh, it's 121.57, so it should be 122. Excuse me. And there we go. It moved up to the second shell. So light at 122 nanometers is exactly the right amount of energy to bring the electron from the n equals 1 to the n equals 2 shell. And if I were to change this to 103 nanometers, that would bring us from the n equals 1 to the n equals 3 shell. Let's see. It's in the first shell, and there we go, up to the third. And so there you have it. I'm going to slow this down. Slow this down a little bit. So there you have it. This is what the Bohr model predicts. In reality, electrons don't move around in predictable circular orbits or spherical orbits for that matter. There are limitations to this model, but this model did significantly help us understand the atom, and it fixed the problem with Rutherford's model that the electron should crash into the nucleus. Anyway, this is a great simulation. I should post this link on Classroom, whatever year this might be. If I haven't already, remind me to do it. This is actually a lot of fun to play with, and it can really help with your studies. Anyway, I hope you've enjoyed this walkthrough, and let me know if you have any questions or comments in the comment section below. Thank you.